Welcome to lecture B11, which is about random variables. And to introduce this topic, I'll start by looking at one of the problems at the end of section 24.5. Let's start with problem 24.5.1. It says graph the probability function f of x equals kx squared, and then in parentheses we're told that the permissible values for x are 1, 2, 3, 4, and 5, and it says k suitable. We'll talk about what that means in just a moment. And then we're also asked to plot something called the distribution function. So let's try to understand what this means. Now, first of all, we're not told what the random variable here is called. So we'll say let the random variable be x, and that's a capital X. Lowercase x here represents the value of the random variable. The random variable is capital X. Now, the first observation is note that x is a discrete random variable. Now, what does this mean? This means that the values that the random variable can assume are separated from each other. You see, the values that x can assume, there's only 5 values, 1, 2, 3, 4, and 5. The other kind of random variable that we will talk about is continuous random variable, and a continuous random variable can assume values over a range, over a continuous range of values. But for a discrete random variable, there are only discrete values that random variable can assume. And so that's the difference. And it's important to, at the beginning of a problem, to note whether it's discrete or continuous, because that will have some bearing on how you pursue the problem. So in this case, we're talking about a discrete random variable, and we're told that the probability function is f of little x here, which is equal to kx squared, and the possible values for little x are 1, 2, 3, 4, and 5. And they say k suitable. Well, now let's talk about what k suitable means, because if we're going to graph this function, then we need to know what k is, and so that's our next question. What is k? Well, let's note the following. Again now, the only values that little x can have are 1, 2, 3, 4, and 5. And so let's just calculate what value f will have for each one of those values of x. So we'll have f of 1 is equal to k. F of 2 is equal to 4k. F of 3 is equal to 9k. F of 4 is 16k. And finally, f of 5 is equal to 25k. Now, what does a little f function mean? What does this probability function means? Well, as its name suggests, the probability function tells you the probability. It's the probability that the random variable capital X will have that value. So the probability that X is equal to 1, that the random variable has the value of 1, is k. The probability that it has a value of 2 is 4k, the value of 3 is 9k, 4 is 16k, and finally the probability that it has a value of 5 is 25k. And those are the only 5 values that it can have. Now, even if you haven't read this section in the textbook yet, I imagine that you can guess how we can find k. If these are the only 5 values that the random variable can assume, and 1, 2, 3, 4, and 5 are the only values, and here are the probabilities in each case, then how do we find k? Well, we simply use the fact that if we add up all of those probabilities, it must be equal to 1. So we say k plus 4k plus 9k plus 16k plus 25k is equal to 1. And 16 and 9 here is 25, and 25 is 50, and then 5 more, so 55k is equal to 1, and therefore k is equal to 1 over 55. So that is the value of k in this problem. And now it would be trivial to plot little f of x. I'll go ahead and do that. I don't really regard this as being, this graph as being very critical, but the next graph is a bit more important. So anyway, here is here's a set of axes. On the horizontal axis we have little x, and the vertical axis we have little f of x. And so if we mark on this horizontal axis 1, 2, 3, 4, and 5, then we could say, okay, for 1 it's equal to k, and of course this is not going to be to scale. Maybe I'll try to make it a little more to scale, so I'll put this maybe down here, and here that would be 4 and 9, and then 16, and for 5 maybe somewhere like this. So that would be a plot of little f of x in this case, but it's important to note, now this function is an increasing function for the permitted values of x at least, but that does not have to be the case for little f. Little f could have been a decreasing function, it could have been oscillatory. There's no restriction on little f, except that when you add up all of the values of little f, all of the non-zero values, then you must obtain 1. So now let's come to the second part of this problem. We've graphed the probability function, we have found k, but now it wants us to do one more thing, and that's to graph the distribution function. Well, what is the distribution function? First of all, the distribution function, which is also called often the cumulative distribution function, is given the symbol usually capital F of little x, and it is equal to the probability that the random variable, which is capital X, is less than or equal to little x. And therefore, if you have a discrete random variable, as we do in this case, then this simply becomes the sum of I'll put it this way. We will sum up all of the values of f of y where y is less than or equal to x. Because remember, at little f of y, if we're talking about a discrete random variable, then little f of y is the probability that the random variable is equal to y. And we want to sum up all the probabilities of the random variable assuming values as long as the value in question is less than or equal to little x. And so that's exactly what this sum says, is that we sum up all of those probabilities for all values y that are less than or equal to x. Now, if y is greater than x, we don't want to take into account that probability, because this distribution function is supposed to be just the probability that the random variable is less than or equal to x. So let's see then how this would go. We'll say so in this case, well, notice that if x is less, if this little x here, if it is strictly less than 1, then, and remember now, here are the probabilities that the random variable has each one of these values. Oh, and I didn't put the I didn't mark the vertical axis to show what those values were, but here this is supposed to be k, and then this is supposed to be 4k. I tried to draw this to scale. I'm sure it's not exactly to scale, but it's roughly correct, I believe. This would be 9k, and so actually my thinking was this: 4k, 8k, 12k. Well, actually we already know what k is, so let me change that. So this would be 4 over 55, 8 over 55, 12 over 55, 16 over 55, 20 over 55, and 24 over 55. That was the scale I was using on the vertical axis, and as I say, I believe the plot is roughly correct. But anyway, if we now glance at that plot, and we can remind ourselves that there is zero probability that the random variable will have a value less than 1, so we can put 0 here. Capital F of x, probability that the random variable is less than or equal to little x, is 0 if little x is less than 1. However, if little x is greater than or equal to 1, but strictly less than 2, then the probability that little f of x is in that range. Now let's think about that. What that means. Little x now is between 1, but it's greater than or equal to 1, but it's not all the way quite to 2 yet. And so the probability that the random variable would have a value somewhere in there, the less than or equal to some value in there, is simply equal. There's, of course, it couldn't have, the random variable could not have the value of, say, 1 1/4 or 1 1/2. But we're not interested, we're not asking for the probability that it has an exact value. We're asking here, when we're talking about the distribution function, we're asking the probability that it is less than or equal to some value. And so the probability, if we add up all the probabilities of the random variable having a value that is less than or equal to some number in this range between 1 and 2, well, there is one possibility there, and that is this one, and we already know that, remember, for 1, the probability is k, which is 1 over 55. So we get 1 over 55. That's the probability that the random variable has a value less than or equal to little x if x is in the range greater than or equal to 1 but less than 2. Now, if we now look at the next step, if little x is greater than or equal to 2, so it's to the right, it includes 2, the range, x could be 2 or anything to the right of 2 up 2, but not all the way to 3. So x is somewhere in this range, and if that x is in that range, then the probability that the random variable capital X is less than or equal to that is equal to this plus this. There are 2 possibilities of the random variable being less than that little x. There's both of these possibilities that must be accounted for. And I believe you see why this is now also frequently called the cumulative distribution function, because now we have to accumulate. In the previous case, we had just 1 probability. Now we have to have 2. In the next case, we'll have 3, and then 4, and so on. So in this case, we add up 1 and 2. We have k plus 4k, so 5k, which is 5 over 55. In this case. And then we go to the next case. If 3 is less than or equal to little x is strictly less than 4, well, then we add up all 3 of these cases, 1, 2, and 3. And so we would have k and 4k, that's 5k, and 9k is 14k, or 14 over 55. And then if 4 is less than or equal to little x is less than 5, okay, now we add up all 4 of these. So we have k and 4k is 5k, and 9k is 14k, and 16k is 30k, or 30 over 55. And then finally, if 5 is less than or equal to x, now we add up all of them, and so we already know we had 30 if we accumulated up to this point. Then we add that last one, and we get 55k, which is 55 over 55, or 1. And so here is the final expression for the distribution function, and now we can plot that. Let's maybe try to do this the same way we did before. Let's say, well, no, let's say 1 and 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1, and 0.0. And this will be little x, and now we're plotting capital F of little x. Okay, and before we continue, I notice now that your book is actually, in plotting the probability function for a discrete random variable, it puts vertical lines, so you can do that. It's not really necessary. The dots are sufficient, but if you like to draw these vertical lines, that's fine as well. So now let's see what we have for capital F of x. So let's have 1, 2, 3, 4, and 5. And for 5, we can go ahead and put a dot here, and then put a vertical line at 1, because if little x is greater than or equal to 5, then our last line says that f of little x is equal to 1. And furthermore, we know that if little x is greater than or equal to 1 but less than 2, so it's going to be equal to 1/55th. So this is going to be very hard to see down here on this scale, but something like this. I'll put a hollow circle there at 2, because we don't want to go all the way up to 2. And we put a solid circle at 1. And then we can also say for any x less than 1, it's 0. So we could put a hollow circle there, and then extend this. And that's meant to show that for any little x that is strictly less than 1, capital F of x is equal to 0. If x is greater than or equal to 1 but less than 2, then f of x is equal to 1/55. If x is greater than or equal to 2 but strictly less than 3, so it's equal to 5/55, which is very close to 1/10. So we can have something like this. And then if x is greater than or equal to 3 but less than 4, we have 14/55. So I guess that is fairly close to, well, what, 0.35 maybe? Let's see. Let me break for just a second. Oops, miscalculated there. It's very nearly exactly, or very close to 0.25. So we go right here. And then the only other one to fill out is 30, or is for x greater than or equal to 4 and less than 5, and that's 30/55, which ends up being about 0.55. So we'll have this. And then again, it's not really necessary, but your book is drawing in these vertical lines here, so we can do the same. And there is the distribution function, or the cumulative distribution function, for this random variable. And there are a couple of important points. There are actually several important points about this graph. Now remember, I told you that for this graph up here, although this is an increasing function of x, it doesn't have to be. That just happened to be the case that they chose for this problem. But on the other hand, capital F of x will always be an increasing function of x. In other words, as x gets bigger, capital F, well, maybe I should say, instead of increasing, it will be non-decreasing. It will never go down as you go from left to right. It may stay constant, as it does here, in between 1 and 2, or in between 2 and 3, or etc., or as it does for any when x is greater than 5, it's constant, but it never goes down. So as you go from left to right on a graph of capital F of x, you'll either go up or you'll stay constant, but you will never go down. That's one characteristic of the cumulative distribution function that you need to know. And that's true whether you're talking about a discrete random variable or continuous random variable. It is non-decreasing as you move from left to right. And two other points that are important about the cumulative distribution function, and they are also true whether your random variable is discrete or continuous, is that as you go to the extreme left-hand side of the graph, that is, capital F of negative infinity will always be 0. And because keep in mind that this value of 0 here, this would extend forever. If we had a negative part to our horizontal axis, it would continue to be 0 forever. And on the other hand, f of positive infinity is always 1. If we kept on going here, this would continue to be 1 forever. So those three facts are true for the distribution function always when you whether your random variable is continuous or discrete. Once again, it's capital F of negative infinity is always 0, capital F of positive infinity is always 1, and capital F is always non-decreasing as you move from left to right. So that introduces us to discrete random variables, and now let's do a similar problem with a continuous random variable. On second thought, maybe it would be better for us to do one more example concerning a discrete random variable, and then to save our examples of continuous random variables for the next lecture. So let's do another one now with a discrete random variable, and this will be problem, actually it'll be a modified version of problem 24.5.6. So the first part of this problem says a box contains 4 right-handed and 6 left-handed screws. And now I'm going to well, I guess I'll just stick with what they have. So it says no, I think I'll change it. So the book actually says 2 screws are drawn at random. I think I'm going to make it just a little bit more complicated and say 3 screws are drawn at random without replacement. And then it asks a number of questions about various probabilities. But what we'll do is instead what we'll ask is the following. I'm sorry. There's one more sentence here missing. So let capital X be the number of left-handed screws drawn. And now is when, that's the same in the book, but now, as I said in the book, they ask you a number of probabilities. For instance, they say, what is the probability x equals 0, probability x equals 1, probability x equals 2, probability 1 is less than x is less than 2, and so on. They ask you a number of different questions about various probabilities, but what I'm going to do instead, this will give us all of that information. But it will also, if we make this modification, I'm going to suggest, it will also give us practice on finding the probability function and the distribution function. So I'm going to ask, what is little f of x, and what is capital F of x? Now, if you have really paid very close attention, then you should be able to answer these two questions. Remember that little f of x is the probability that the random variable will have the value little x. And capital F of little x is the probability that the random variable has some value less than or equal to little x. So just using those two definitions right there, you should be able to solve this problem. And I very strongly suggest that you stop the video and try to solve it. And then when you think you've done it, then come back and let's work it all together. Okay, so the first thing to do is to find little f. And as we said, this is the probability. Now, when you're talking about a discrete random variable, little f has a slightly different definition when you're talking about a continuous random variable. So now actually capital F is defined the same, well, it has the same general idea behind it for both discrete and random and continuous random variables, but little f actually is different for the two. It's slightly different. And so, but recall that we're now dealing with the discrete random variable. So it's the probability that the random variable capital X has the value little x. And now let's figure out what that will be in this case. Well, if first of all we can note that capital X is representing the number of left-handed screws, and the number, the lowest value that a number can have is 0. So we don't have to consider any values of X that are less than 0. We don't have to consider any negative values at all, because certainly the probability that the number will turn out to be negative is going to be 0. So the first number that we have to really consider here is x equals 0. And then the next possible value that we could obtain for the number of left-handed screws drawn, of course, would be 1. The next would be 2. Now remember, we are drawing 3 screws at random without replacement. And so the last value that we have to consider is 3. Those are the only 4 possible values that the random variable capital X could have. We could get 0 left-handed screws, we could get 1, we could get 2, or we could get 3. Those are the only possibilities. So now we just need to find these probabilities. So if you haven't done this already, I encourage you once again now to try to stop and figure out each one of these probabilities, and then let's do it together. Okay, so first we want to know the probability that you'll get 0 left-handed screws. Well, of course, there's only one way that can happen, and that is if each one of the screws drawn is right-handed. So the probability that the first one is right-handed, since you have 4 right-handed and 6 left-handed, then we can say probability that X is equal to 0. Actually, back up. I'll say little f of 0 equals probability that capital X is equal to 0. And again, the only way that could happen is if all 3 of the screws drawn are right-handed. Now, the probability that the first one is right-handed is 4 out of 10. And then the probability that the second one would also be right-handed would be 3 out of 9, because there would only be, if the first one drawn was right-handed, there would only be 3 left, and there would only be 9 total screws, so 3 out of 9. And then the probability that the last one would also be right-handed would be 2 out of 8. And so we have a total here of 4 times 3 is 12, times 2 is 24 over 720. That's the probability that there would not be a single left-handed screw drawn. 24 out of 720. Now we want to figure out the probability that there is 1 left-handed screw drawn. Well, there are 3 ways that we could get 1 left-handed screw. We could have the first one left-handed and then the next 2 right-handed. Or we could have the first one right-handed, the second one left-handed, and then the third one right-handed. Or we could get each of the first 2 is right-handed and then the third one is left-handed. So there's 3 different ways that we could obtain exactly 1 left-handed screw. And let's go ahead and find out the probabilities for all 3 of those outcomes. Okay, so the first one we were going to look at, we said, is P of left, right, right, plus P of right, left, right, plus P of right, right, left. Those are the 3 ways that we could come up with exactly 1 left-handed screw. And now let's look at the probabilities for each. Okay, the probability that the first one is left-handed will be 6 out of 10. And then the probability that the second one would be right-handed, given that the first one is left-handed, would be 4 out of 9. And then another right-handed would be 3 out of 8. Now the probability of right, left, right, well, the probability that the first one is right is 4 out of 10. And then the probability that the next one would be left would be 6 out of 9. And then the probability that the last one would be right would be 3 out of 8. And finally, for right, right, left, we get 4 out of 10 times 3 out of 9 times 6 out of 8. And notice, as we've seen in several cases like this already, all 3 of these numbers are really the same. We have 6 times 4 times 3 in the top. It could be in different order, but it's always 6 times 4 times 3, and 10 times 9 times 8 in the bottom. So we have 6 times 4 is 24, times 3 will be 72, And 72 times 3 will be 216. And then in the bottom we have 720. So 216 over 720 is the probability that the number of left-handed screws drawn will be 1. And now let's look at the probability that that number will be 2. Well, that could happen in the following way. We could say right, left, left, or we could have left, right, left, or we could have left, left, right. Those are all the ways in which we could have 2 left-handed screws. Now, once again, these 3 probabilities that we calculate will all be the same, but let's just make sure that that's true. Okay, so right, left, left. Probability of the first one is right is 4 out of 10. And then the second one would be left would be 6 out of 9. And then that the next one would also be left would be 5 out of 8. Probability that the first one would be left is 6 out of 10. Probability the next one would be right would be 4 out of 9. And then that the last one would be left would be 5 out of 8. And then for the last set here, left, left, right, for that outcome, the first probability is 6 out of 10. The second one is 5 out of 9. And the last one is 4 out of 8. And you can see indeed in the top, 4 times 6 times 5, 465, 465 is always the numerator, and the denominator is also always 10 times 9 times 8. So all 3 of these are the same. And what is it equal to? Okay, 4 times 5 is 20, times 6 would be 120, times 3 is 360 over 720. And of course that's equal to 1/2, but I think I'll just leave it as 360 over 720 so that we'll have a common denominator of 720 for all of these values here. So we have 360 over 720. And now finally, little f of 3 is the probability that we have 3 left-handed screws, and there's only one way that could happen, and that's left, left, left. And so the probability of that is 6 out of 10 times 5 out of 9 times 4 out of 8. And so we get 120 over 720. And so that's it. Unless we have made some error, here is the expression for little f of x, which is the probability function. Now, I'm not going to even try to go back and check this, because one good thing about going ahead and calculating the distribution function is that it will give you, the calculation of the distribution function gives you a partial check on your work for the probability function. You'll see what I mean by that in just a moment. So now let's calculate capital F of x. And notice that indeed, if little x is any number less than 0, we can observe, we'll say if little x is less than 0, then this is 0. Because if we add up all those values where little x is less than 0, well, there are no values where little x is less than 0, so if we add them all up, we get 0. And remember that we said that for the distribution function as we go to the left on the graph, as x goes to negative infinity, f of x must be 0. So this is, so far, our expression for capital F of x looks good. Now, the next case to consider is 0 less than or equal to little x less than 1. And then let's go ahead and write out the other cases. If 1 is less than or equal to little x is less than 2. If 2 is less than or little x, less than or equal to little x is less than 3. And then finally, if 3 is less than or equal to little x. And now we need to figure out each one of these. Okay, so if little x is greater than or equal to 0, but it is strictly less than 1, well, there's one way that the random variable could be less than or equal to a number that is in that range, and that is if it is equal to 0. And the probability that it is equal to 0 is 24 over 720. So we have 24 over 720 for this value. Now, what about if little x is greater than or equal to 1, but strictly less than 2? Well, there are two ways that the random variable could be less than a number that falls in that range. Either the random variable could be equal to 0, or the random variable could be equal to 1. Because in either case, it would then be less than or equal to any x that satisfies this requirement here. So we need to add up the probabilities that the random variable is equal to 0 and that it's equal to 1. And so we get 24 over 720 plus 216 over 720, or we get 240 over 720. 240 over 720. Now, what if little x is greater than or equal to 2, but strictly less than 3? Well, there are three ways that the random variable could have a value less than x, an x that satisfies that. Less than or equal to an x that satisfies that. And those three possibilities would be that the random variable is equal to 0, or the random variable is equal to 1, or the random variable is equal to 2. And so we need to add up all three of these possibilities. And remember, that's 240 up there, and 240 and 360 is 600. So we have 600 over 720 for this one. And finally, if x is any number that's greater than or equal to 3, and we want to know the probability that the random variable is less than or equal to x, well, it has to be, right? Because it can only be equal to 0, 1, 2, or 3, and so the probability that it's less than or equal to some number that itself is greater than or equal to 3 is 1. Now, does that agree with the above? If we add up all the probabilities, well, we already know if we add up these top three, we get 600 over 720, and then if we add to that 120 over 720, indeed it does turn out to be exactly 720 over 720, or 1. And so the fact that those are all adding up to exactly 1 does indeed help us to feel confident that our work up here for little f of x is indeed correct. So, and notice, as we said before, as we go to the extreme left on the graph, if we plotted this function capital F of x, as we go to the extreme left, we have a value of 0. We go to the extreme right, we have a value of 1. And in between, as we go from left to right, as we go to increasing values of x, this function is it never goes down. It's getting, it's equal to a constant for a while, and then it goes up to 24 over 720, then it's constant, it then goes up to 24 over 720, then it's constant, then 600 over 720, and then finally it goes up to 1. So everything looks good here, and I think it's safe to assume that both of these answers are correct. So that is how you find the probability function and the distribution function for a discrete random variable. And now let's try to let's consider some problems on this topic. Okay, so both of our problems for the take-home or at-home part of the quiz will deal with the following situation. We have 3 fair coins, and what we mean by fair coins is that these coins are not in any way weighted so that you would get some kind of unfair result. In other words, for each of these coins that we toss, the chances of heads is 50%, the chance of heads is 50%, the chance of tails is 50%. That's true for each one of these coins. So 3 fair coins are tossed simultaneously. Let x be the number of heads. And so x is clearly a discrete random variable because it could only assume the values of 0, 1, 2, or 3. If you toss 3 coins, you could either get 0 heads, or 1 head, or 2 heads, or 3 heads. Those are the only 4 possibilities that you have. And so in problem B11-1, you're asked to find little f of little x. And you can see the choices here: A, B, C, and D. And I believe everything is pretty clear there, but I'll read it quickly for you. A says f of little x equals 1/8 if x is equal to 0, 3/8 if x is equal to 1, 3/8 if x is equal to 2, and 1/8 if x is equal to 3. In choice B, we have f of x is equal to 1/8 if x is equal to 0, 1/8 if x is equal to 1, 1/8 if x is equal to 2, and 1/8 if x is equal to 3. In C, f of x is equal to 1/4 if x is equal to 0, 1/4 if x is equal to 1, 1/4 if x is equal to 2, and 1/4 if x is equal to 3. And finally, choice D, little f of x is equal to 0 if x is equal to 0, 1/8 if x is equal to 1, 7/8 if x is equal to 2, 1/8 if x is equal to 3. And again, all of those were choices for little f of x. And now for problem B11-2, in this one, as you would probably expect, you're asked to find capital F of x. And choice A says capital F of x is equal to 0 if x is less than 0, 1/8 if 0 is less than or equal to x is less than 1, 4/8 if 1 is less than or equal to x is less than 2, 1/8 if 2 is less than or equal to x is less than 3, 0 if 3 is less than or equal to x. Choice B says 0 if little x is less than 0, 1/8 if 0 is less than or equal to x is less than 1, 4/8 if 1 is less than or equal to x is less than 2, 7/8 if 2 is less than or equal to x is less than 3, and 1 if 3 is less than or equal to x. C says negative infinity if little x is less than 0, 1/8 if 0 is less than or equal to x is less than 1, 4/8 if 1 is less than or equal to x is less than 2, 7/8 if 2 is less than or equal to x is less than 3, and infinity if 3 is less than or equal to x. And finally, choice D, 1/8 if x is less than 0, 1/8 if 0 is less than or equal to x is less than 1, 1/8 if 1 is less than or equal to x is less than 2, 1/8 if 2 is less than or equal to x is less than 3, and finally, that's supposed to be 1/8 again, 1/8 if 3 is less than or equal to x. So those are the 2 problems, and that concludes lecture B11. And then, as I said, we'll have, as usual, at least one other problem in class. So good luck.